Thank you. So today, this topic is multiple interactive proof in quantum computing settings. And so interactive proof is one of the central topics in computational complexity theory. And before that, this is a joint work with Thomas Bidiek at MIT, and the paper is available online. So, so interactive proof is a computational model which characterizes how difficult or how easy it is to verify someone's claim in the when you can interact with someone who can provide any proof to your question. So this is kind of a generalization of the class NP, if you know, if you're familiar with complexity classes. In this class, you can ask question and receive an answer instead of just receive an answer and verify this static string. So this is more interactive setting, and so the important question was which problems or which kind of claims can we verify efficiently with by interacting with someone who can compute anything. So we are not concerned with how difficult it is to come up with proof, but we only consider the difficulty of verifying the proof. So to model that, we allow any computation to a party called prover who provides proof, and we are only concerned with the complexity of the verifier who has to distinguish the case where prover is making the correct claim and the prover is making a false claim. So in an interactive proof, we require two properties. One is completeness. If the prover's claim is true, then the prover must have some strategy to make the verifier accept the claim with high probability. And the other property is soundness. So if the claim is false, no matter what the prover does, the verifier must be able to reject the claim with high probability. And it's known that the class of problems which can be verified efficiently in this setting is equivalent to polynomial space computation, although we only allow polynomial time computation. So this is for verifier. So this is a vast increase of computational power. So this characterizes the power of interacting. Now, there was a variation of this model called multi-prover interactive proofs. And in this setting, the verifier can interact with not only one prover, but more than one prover, and who can't communicate with each other. So as a metaphor, we can imagine we lock several provers in separate rooms, and we ask questions one by one. And by doing this, we can cross-check the prover's claims or prover's certificate without worrying they may be colluding behind. So this model is trivially at least as powerful as single prover model. And And this model turned out to be actually much more powerful than polynomial space under some complexity theoretic assumption. So this multi-prover interactive proof turned out to be equivalent to non-deterministic exponential time computation. So this includes so deterministic exponential time computation is already a superset of polynomial space computation, and moreover, we allow non-determinism to them. So it's pretty big class. Although we don't know if really if polynomial space is really not equal to non-deterministic exponential time, but we expect this is quite big. And also, we know the same holds even if we restrict the model to quite a lot. So even if we only have access to 2 provers, and we have to ask questions and receive answer in 1 round, and we only allow exponentially small one-sided error, so this class is still equal to NEXP. And there were further improvements to this result, and later these results led to the PCP theorem, a big theorem in complexity theory, which have many applications to various which has many applications in inapproximability results of various optimization problems. So this is all classical word, not quantum word. But so now I will quickly explain relevant quantum part. Actually, to this talk. And so we won't use any definition from here, but I'd like to emphasize some aspects of quantum information. So quantum state is just a matrix, and you can't extract information from by just looking at the quantum state. You have to do some measurement to extract information to the quantum state. And so action is another kind of matrix, and we can define the probability of the action given the state. And measurement is just k-tuple of actions, which is guaranteed to give some probability distribution over these k events. And if we have 2 people who share a state, we have a composite system made of 2 subsystems. So, and in this case, the dimension of the composite system is the product of the dimensions of the 2 subsystems. And actions on each subsystem are composed by using the Kronecker product of the matrices. And by very simple math, we can check that if we fix one measurement on one site, on one subsystem, and we do some other measurement on the other subsystem, and if we consider only the marginal distribution of the outcome of one subsystem, then this marginal distribution doesn't depend on what we do in the other subsystem. And
this is a requirement, or that's a property?
this we can prove this property by using what I said.
Yeah,
So this is a property. This is not a requirement. So and this is sometimes called no signaling principle. So just by sharing a quantum state and measuring one site, one subsystem, we can't affect the probability distribution of the outcome of measurement at the other subsystem.
That's assuming that it's a tensor product state.
No, we don't assume. We don't assume anything about the state.
So if you have an APR pair, and you look at you measure one.
Yes, even in that case, yes. So okay, so yes. So so this holds in any state, and if you know about okay, so the question is yeah. So in that case, in the case of EPR pair, if you look at the outcome of the first subsystem, then you know something about the outcome of the second outcome. Oh.
What is the meaning of this? That one outcome does not depend on the measurement done in the other subsystem.
Okay. So. Okay. So the meaning is so outcome may depend on outcome can be correlated, but what I meant here is the distribution of the outcome at the first subsystem doesn't depend on. So if we so after we so we only defined what happens if we measure both subsystems, but in other words, this means the marginal distribution of the outcome at one subsystem is well defined even if we don't specify what we do at the other subsystem. So this holds in any subsystem. So but the joint distribution have some correlation depending on your state. I forgot to say I forgot to say this part. So a quantum state is a certain matrix, and special case is diagonal matrix, and this is a probability distribution. So we can consider shared random variable as a special case of quantum state. So even in this case, the outcome of the two measurements at different subsystems may be correlated, but this doesn't contradict the no signaling principle. If we only look at the distribution of the one outcome, it doesn't depend on what we do at the other subsystem.
So one way to say that may be that if Alice and Bob each have their own halves of these two subsystems, and Bob either measures or doesn't measure his side, and Alice performs some measurement, she's trying to figure out whether Bob made a measurement. But whatever she sees won't give her any information.
Yes. Or if Bob does certain measurement or other measurement, right. That doesn't affect what Alice sees, unless we know the outcome at the Bob's side. In that case, there might be different correlations. Okay, so in the multi-prover interactive proof system, we assumed the provers won't communicate with each other after the interaction starts. But before the interaction starts, they can do anything. So it's natural to consider they exchange some information and they share certain state. In the classical world, all they can do is share certain random variable. So in some arbitrary distribution. But it's easy to see this won't affect the behavior of optimal provers. So if there is some nice thing the provers can do by using shared randomness, they can fix the value of this random variable to certain one value to get as good behavior as before. So by convexity. So this is so in the classical world, whether they communicate before the interaction or not doesn't matter. What matters is they do optimal thing. But in the quantum world, they may send quantum state. In this case, it's known that it matters. And one of the examples is called the magic square game. So imagine this toy problem of fitting a 3x3 grid with zeros and ones so that each row has even parity and each column has odd parity. This is clearly impossible by considering the parity of everything. However, you have two friends, Alex and Bob, who claim this is possible and try to convince you. How? So first you lock Alex and Bob into separate rooms, and you choose one line, either row or column. So there are 6 possibilities. And one cell in that line, there are 3 possibilities. And ask Alice the contents of tell which line you chose to Alice, and ask Alice the contents of the 3 cells. And tell Bob which cell you chose, but without telling which line. And ask Bob the content of that cell. And you accept the claim if the parity of the 3 bits in Alice's answer is correct. So even if you chose row, and odd if you chose column. And also, for the cell you asked to both, the answer must be the same. So this can be formulated in this way. So you are a verifier, and Alice and Bob are provers. And if they don't share anything or share random variable alone, it's easy to see they can't satisfy all the constraints. So if, for example, you choose the 18 possibilities, one of the 18 possibilities with equal probability, the optimal strategy makes the verifier accept with probability 17 over 18. At least in one case, you catch the cheating. But if they are allowed to share quantum state, there is a strategy which makes the verifier accept with certainty.
You're going to show it or not? You're going to show the strategy?
No, I'm not going to show. To do it, actually, yeah, technically, I only need what I stated before, but I guess it's, so if you remember everything I said, I can show that.
So, so just a question about it. They are allowed to measure the state before answering the verifier.
Yes, yes. So they first share some state in a quantum setting. They first share the state and receive the question and measure their share of the state depending on the question. So the way to measure, the measurement can depend on the question, and decide the answer based on that. So this makes a difference. So whether we live in quantum world or classical world makes a difference, even though from the verifier's point of view, everything is classical. So this was a big surprise to physicists in 60s, and this example is a newer example, but there were examples showing this fact in 60s, and this this phenomenon was studied in physics, but we are now looking at this question from computer science point of view, and more specifically from complexity theoretic point of view. So before that, okay, I'd like to emphasize that we still don't allow communication, even if we allow sharing quantum state. So because of the Noetherian principle, sharing quantum state alone doesn't allow the provers to communicate anything. So Richard Cleve, Peter Hoyer, Ben Turner, and John Matras pose a question of identifying the computational power of this model. So it's the same as the classical multi-prover interactive proof systems, but now we allow provers to share any quantum state before the interaction starts. So this question was kind of okay. So one intuition might be we allow provers to do more, so it must contain MIP. But this reasoning is not true, not correct, because for example, if we allow provers to do more, that can decrease the power. For example, if we allow provers to communicate to each other, then from the verifier's point of view, they are the same as single prover. So allowing more to provers have two aspects. One is dishonest provers may use this additional power, and therefore the class might be smaller than the original. Or honest provers might use this for verifier's benefit, and so the class might be bigger than the original. So so we didn't know the relationship between entangled case and completely classical case.
I guess it's the monotonicity there is just that it can increase both the completeness probability and the soundness probability.
Yes.
That's why it's not clear.
Yes. 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 So yes. Yes. This affects both. Yes. So this increases acceptance probability in any case. But the problem is we want to make acceptance probability in the true case, and we want to keep acceptance probability low in the false case. So that's why it's not clear the relation between these two is. So before our work, there were studies on this class, and this is part of it. So first of all, train provers and use just one prover. In that case, we don't care what they share. And in that case, we get single prover IP. And Cleve and others found an evidence that indeed this class does not contain classical MIP in with a easy reason. So okay. They showed an evidence that the reasoning I said before, so MIP star must be at least as powerful as MIP, is broken. by showing with certain restriction to the verifier, we can show entangled version is inside deterministic exponential time, but without entanglement, without sharing quantum state, it's still non-deterministic exponential time. And about this MIP star, so some people try to construct protocols which is good, which is still good even if we allow provers to share quantum state, but with very weak sense of good. So so if we allow very large one-sided error, exponentially close to 1 soundness error, then this class is known to contain non-deterministic exponential time. And also, if we restrict the verifier to 1 round, so ask question and receive the answer, in this case, we know this model is seems to be more powerful than single prover by showing this class contains piece polynomial space. If we only use single round and 1 prover, then we get complexity class AM, and this is conjectured to be much smaller than P space. So our result is we solve this open question. MIP star contains NEXP. We need 3 provers, polynomially many rounds, but we achieve exponentially small error instead of exponentially close to 1. So this was the first protocol which works for anything bigger than polynomial space and has non-huge error. So our approach was kind of quite natural. So previous approach was previous results were based on previous results which has huge error probability was based on this approach. So take existing protocol which doesn't consider the existence of take existing protocol for MIP without star, so which doesn't take into account the provers may share some quantum state, and change it a little, and analyze the modified protocol, but use the classical soundness as a black box. So basically, we reduce the task of proving the stronger soundness against entangled provers to proving the soundness of classical provers. And the soundness against soundness with the classical provers was already known, so we can do this. And this proves the soundness against cheating entangled provers. And the analysis doesn't depend on the detail of the protocol itself, because we just use the fact that it's sound against classical provers. But this had a apparent limitation of giving pretty large error probability. Our approach is different. So take some existing classical protocol, and in our case, we took the first multi-proof interactive proof system for non-deterministic exponential time by Babai, Fortnow, and Lund. And we basically went through the soundness analysis of it, and we did it, but in presence of entanglement among provers. So this goes through the analysis. So analysis depends on the protocol heavily. So this is a natural approach, which someone should do, and we did it. So the most important part of the protocol of Babai, Fortnow, and Lund is called multilinearity test. And so the purpose of this test is to force provers to act like some multilinear function from n variables to one variable. Here, by multilinear, I mean a polynomial function which, where no term contains any variable more than once. So to some people, this is multi-affine function. But I think in this context, it's more usual to call it. It's usually called multilinear. And the test itself is simple. The verifier chooses one coordinate and 3 points from this f to the n, so that all the coordinates except for the chosen one are the same for these 3 points. So they're on a on one x parallel line. And ask what the value of this at this point. And after receiving this answer, the verifier just checks they are indeed on the same. So the answer is indeed the same line, because by definition, multilinear function, if we fix all but one variables in multilinear function, we get a linear function, but I mean affine function, or polynomial of degree at most 1. So so we can check it. So they showed if provers indeed choose their answer according to the same function, and they pass this test with high probability, then this function is indeed close to some multilinear function. And so this part is basically, if everything is reasonably small, then this is pretty good, pretty close to some multilinear function. So to construct the whole protocol for non-deterministic exponential time, they combined this test with other tests. But this part is the most important part in our this part is most involved part in their analysis, and also this part is the most crucial part in for our purpose too. And of course, for us, the problem is we don't have the guarantee that provers choose their answers according to some function. So it's easy to remove the restriction of this same function. So first, if we consider the case where provers may use different functions, we can still modify the test so that we can deal with that part. So we modify the protocol so that the verifier now do the test I described before, and consistency test. So sometimes the verifier chooses just one point and asks the same point to all 3 provers, and test all the answers are equal. So in this case, it's not hard to see, even if each prover chooses her answer according to some function, but they may not be equal. The same conclusion holds.
So you will do epsilon will be polynomially small, and you will do it by sequential repetition. You'll ask them. You'll run this test n squared times.
Yes, yes, yes. So so this error is yes. So we get error polynomially close to 1, but we can repeat this whole protocol polynomially many times to make it exponentially small. Of course, we couldn't use the same thing if we had error 1 minus exponentially small, because then we had to repeat everything exponentially many times. So, and now, of course, for our purpose, this is still this is a slight improvement, but not much, because the provers, so provers may choose the answer by measuring their own part of quantum state. So it's not just a function. So if we think about it, even if we restrict our attention to the special case where the shared quantum state is just a diagonal matrix or shared randomness, there is a problem. So because now, now we can't say they use some common multilinear function, because they might use some probabilistic mixture of multilinear function, and verifier has no chance to detect that. So a nice way to so we need some way to state this nicely in a way that extends to quantum setting. So we need some way to state this conclusion. So now we can consider in this way. So we start with a prover who take some point x and shared random variable and answer one value, scalar value. If provers pass the combination of multilinearity test and consistency test, then with high probability, then we can replace this prover by more benign prover whose behavior is quite restricted. Namely, the prover just look at the randomness and choose a multilinear function without looking at which point she is asked, and then just answer this value. And all we want to say is if the test, if the provers pass the test with high probability, we can change from this general prover to this much more restricted prover without affecting the output much.
This randomness is shared by the prover.
Shared, yes. So we don't change the shared random variable at all. We just change how the provers use. And once we formulate, and actually this reformulation is doesn't tell you anything new per se, because shared randomness can be eliminated in the at the first step of a proof. But by formulating what we want to prove as in this form, we can consider the case of entangled provers. So now this is the this is what we want. This is the analog, quantum analog of the soundness of multilinearity test. So if we start with a prover who receives a point in this f to the n, and also has her share of a quantum state and measure this depending on this point and receive one value. And if they pass this combination of multilinearity test and a consistency test with high probability, then we can replace this prover by this much more restricted prover who decides which multilinear function to use without looking at the point. And by affecting the output much. So I won't. Obviously, I don't have time to prove this, but this. So coming to this statement was kind of non-trivial step, and also and proving this statement is actually turned out to be much more involved than the classical case.
So can you at least say some things about so you're not going to prove it?
Yes, but I'm going to say something about how to prove this. But before that, so after proving, if we have proved this, we can indeed construct a protocol for non-deterministic exponential time in almost the same way as what Babai, Fortnow, and Lund did. So we take some next complete language, and we describe the constraints on the solution to this problem by using exponentially many constraints. And we require the provers to hold a multilinear extension of this solution. And after that, the verifier chooses one of the three tests: multilinearity test, consistency test, and the test known as subseteq test, which allows the verifier to test exponentially many constraints, exponentially many simple constraints. So, so the rest is basically the same as Babai, Fortnow, and Lund. Now, sorry. So the soundness proof of this whole protocol works like this. So because the strategy passes the multilinearity test and consistency test with high probability, these provers can be replaced by restricted provers. And now, in the third test, subseteq test, actually the third prover is asked different kind of question. Sorry. Yes. So, but because these two provers don't know which test they are in, so their behavior can still be described in this restricted form. And now these two provers measure the quantum state before looking at anything new, anything from the verifier. This entangled state, this quantum state is just used as a shared randomness. So, so now we can apply the classical soundness of the third test, and we are done. So,
Can you go back just one second? So is there a reason why you don't use the third prover as before to ask the third point? Why not use it?
oh, so to do next, we sometimes need to test multilinearity, and we
okay. But when you do multilinearity, you do the
we ask 3 points, one to each. But in subseteq test, we have to do something completely different to one of the provers. Yes. now the most difficult, most involved part is to prove the soundness of multilinearity test in presence of entanglement. We basically follow the original original proof outline by Babai, Fortnow, and Lund. But we generalize each step in the proof in a suitable way, and we had and it's not trivial to choose the right one because there are so many plausible-looking generalizations, and most of them didn't work, at least when we tried. So, but the main idea is this. So originally, each prover has some measurement for each point in f to the n, and these measurements have an outcome, scalar as an outcome. Now we do one step of transformation and get a measurement which depends on only x2 to xn, so not x1. And outcome is a linear function or affine function, which only depends on x1. And by repeating this process, we eliminate the dependence of measurement on the input one by one. And at the last stage, we get just single measurement, which produces a whole multilinear function. And in each step, we we use not measurement, but we allow a measurement to give up. So we add one special string, which means this virtual strategy gives up in doing anything useful. And so we have to transform these measurements from this. We have to create this measurement from these measurements by affecting too much to the outcome. So and this how to measure this similarity between two measurements was quite difficult to choose. We tried many things, and it turned out that one particular choice worked quite well, and it's called inconsistency between two submeasurements. We call it inconsistency. So we maintain two submeasurements don't confidently give different choices. So if one of them give up, it's fine, but we care about the probability which both of the measurements claim some outcome, but they are not consistent. And through the induction, we maintain the inconsistency is small, and also the probability of giving up is small in different order. And by repeating two different operations to submeasurement, one of which reduces the dependence on one variable, but inconsistency blows up polynomially. So if we repeat this n times, we get exponentially large inconsistency, so it's not useful alone. And we interleave this process, this pasting process, with self-improvement process. So by self-improving, the inconsistency decreases to a function of the acceptance probability of the original strategy. And probability of giving up increases slightly, but not too much.
The self-improvement doesn't cost anything, right? Like it's like in the original BFL. If you have a large agreement, then you agree almost everywhere.
Yes. So this self-improvement is weaker than that, and it's it's necessarily weak. So even if yes, so original self-improvement lemma showed if we have some function which is mildly close to a multilinear function, it must be very close to a multilinear function. But we can't say that even in the presence of shared randomness, because our random function might be just mildly close to one multilinear function. Okay. A function might be completely a multilinear function with some probability 80%, and with probability 20%, it might be completely random. So in that case, we can't improve this probability 80% to anything better. So we need something to give up. So this giving up is needed to make this statement true. So this operation possible.
So can you at least explain, suppose the function was just in one variable and you have measurements depending on the point, how do you transform it to a linear function that does not depend?
Okay, so I'm not going to explain that, but in self-improvement, we basically choose the target, so the desired measurement by as an optimal solution to certain convex programming, and we analyze this this optimization, this convex programming in geometric way to show it indeed has a desired property, but
but in the at least the proof may be extremely complicated, but it's a statement in the case that n equals 1 is simple, right? You have three provers. You ask them, they are
oh, I see.
Supposedly they have a linear function, but they can do what they want with it. And you ask them specific points to evaluate their functions on, which they can use in the measurements initially. And what you're saying is that you can imitate their behavior in such a way that they make measurements without looking at the input points they are asked about, and their behavior is still the same. So that's a reduction. That's a reduction you're doing.
Yes, but so to reduce the dependence on the input, we need pasting, and this this makes the probability of giving up larger. So
but suppose n was just 1.
Yes.
N is 1, so you have only
in that case, yes.
So how do you reduce the dependence? Don't worry about the time. If
Sorry.
I'm slowing you down, then you don't have to. N equals 1. It's a test of linearity. It's an obvious test. With 3 points, and you want to check that they are.
Yes.
Initially, they can use the points to do the measurements, and you have a transformation, magical transformation, that makes them look as if they are behaving the same, even though they do the measurement before seeing the query. How does it work? What is the convex program coming in here, or where is it?
Okay. In the case of single variable, actually, the self-improvement part doesn't give you anything useful, because after applying self-improvement, the inconsistency decreases to a function of epsilon, but epsilon is the quality of the strategy in the first place. So the probability that they are rejected by this test. So so the guarantee of this part. So basically, we increase the error in both steps. So
yeah, but what is this? So I'm asking something very basic. You have a transformation. Given just that this linearity test is passed with very high probability, 1 minus epsilon. That's all you know about their behavior, which does depend on the query. You have a way of transforming these provers to different provers who first measure without looking at the input query.
yes.
And then they sample the linear function, and then they give answers, and it looks the same to the value.
It looks the same in so okay. It looks the same in so it introduces some error, and
So can you say in what sense it looks the same, and what can you give some mathematics about this? What's happening? I mean,
Okay.
somebody else understands it.
I'm not sure, but I think so. You have a different measurement for every point. But since there is only one coordinate, you just take some measurement that is close to all of them, and it introduces error.
Yeah, so you have
but then you have
that
one
there is
measurement that you apply no matter what the input
you
is.
have to prove that such a measurement is close to all.
But in one dimension, if they are very close to each other, not in one, if there is only one dimension, if they are very close to each other, so then
Not
it means
very
that
close,
all
they are consistent. The linearity test passes.
yeah,
Means they have to be closer.
they must be
linear
close.
function because most of them.
Right.
So then if they are close to each other, you just take a measurement. Actually, you can even take one of them probably in one dimension, right? Probably.
So
Yeah, but one
like
of
a
them,
random one.
but one of them still uses the query. Each one of them does use the query to do the measurement.
No, but for each query you have a measurement. Just like one of these measurements at random. And I think
Um,
but
yes, so
it's
they-
self-improving.
So I understand, yeah, but is that what you're doing? So for one dimension, n equals 1, are you
Yes.
taking just a random measurement of one of the queries?
So-
that will be enough.
So no, we need to combine at least two measurements to get a linear function, affine function. So how we do pasting is okay. In some sense, we take two different points at random and perform the first measurement, the measurement corresponding to the first point, and this gives you some post-measurement state, which I didn't explain. But then we perform the second measurement to this post-measurement state, and
So you need to because it's a linear function, right? So that's because it's 2 degrees of freedom. That's
yes, yes.
But it's possible that after the first measurement, the state is fixed. Right?
The state is sorry.
The post-measurement state may be fixed by now. Maybe you.
May be
Well,
fixed,
anyway,
but
you measure according to one random point.
Yes.
You measure whatever remains. Using a second random point, this gives you a line, and you use this line.
yes, yes. So in general, if we have unrelated measurements, measuring one, performing one measurement and performing the other to the post-measurement state may not give you anything useful in the second measurement because post-measurement state might be completely different, very different from the first state. But in our case, we can use, we can prove that this is not the case. So using the post-measurement state still gives you some useful information, some useful answer to the second question if this strategy passes the test with hyperability. But yeah, so and it increases the error. But it gives you an affine function. And yes, so actually, as Avi already said, self-improvement lemma already exists in Babai, Fortnow, and Lund proof. And also, pacing lemma is also used. And so this interleaving structure is from their proof. But the detail of each lemma is much more involved than the original proof, which I can't go into.
So I can ask the self-improving lemma, does it use local information like on a line, or does it use globally all the information on all the space? In the convex program, is it analyzed only on one line, on one small subset, or the space together?
In self-improvement, we make the resulting submeasurements locally. And what we want to guarantee is global measurement, so global thing. So inconsistency is defined as actually the average over all the choice of the input. So we need to analyze the overall behavior of them. But the submeasurement itself is defined locally. So this is how we prove the soundness of multilinearity test in the presence of entanglement. And we showed NEXP is still contained even if we allow entanglement between provers, but we need 3 provers and polymerically many rounds. And in our proof system, honest provers are classical because we basically use a Babai Fortnow Lund proof system. We redid the soundness analysis in more general setting. And we can transform this protocol to 4 prover 1 round proof system with polymerically close to 1 error, or polymerically many provers 1 round with exponentially small error.
So these transformations in the case of honest provers, are they classical, the honest provers?
Honest provers, yes, they are still classical. Yes. And here are some open questions. So we analyzed the multilinearity tests, but there are other properties which are studied in the context of classical multi-prover interactive proofs and PCPs. So what about these other tests? And also improve the parameters of MIP star, like number of provers or number of rounds and error at the same time, or reduce the answer length. And reducing the answer length has a bearing to the PCP theorem in the classical case. So we don't have a good application of entangled version of PCP theorem, but there may be something. And this was completely about preventing the dishonest provers from using entanglement to cheat the verifier. But there is a possibility that actually there is a positive use for entanglement. And for example, we don't even know whether Hortin problem has MIP star system, but probably no one expects that, but we don't have a proof it doesn't. So we are still far from complete understanding of this model. That's all. Thank you for attention.